Okay, perfect. Okay, welcome everybody to another MCRN Colloquium. Today we're really lucky to have Dr. Brian Buma. He is the Director of Climate Innovation and a Senior Climate Scientist at the Environmental Defense Fund and a National Geographic Explorer. He's focused a lot on raising money for environmental research, funding a variety of scientists for multiple objectives. A lot of the work that he does at EDS has a lot of real-world impacts, looking for practical solutions for the climate crisis. And today he's going to talk about some of that practical work, in particular, addressing the positive feedback of increasing wildfire emissions due to climate change using new satellite technologies and ideas. And I think in particular, interesting new satellite constellation being developed called FireSat. So with that, please take it away, Brian.
Thanks. Yeah, thanks. It's nice to be here. Nice to see everybody. I'm based in Boulder along with a lot of the in-car people. So yeah, great to call in. So today, yeah, I wanted to share some of the work that we are doing at the Environmental Defense Fund in collaboration with a couple other groups, as you'll see, Earth Fire Alliance and Muon, looking at new satellites. The talk is sort of structured across at framing the challenge of wildfires. So if you're not active in the wildfire space, hopefully it's new and interesting. The challenge of increasing wildfire emissions and what that means for climate. And then some new satellite technologies. The one that I'm most familiar with is called FireSat. That's where this picture comes from, which is run by Earth Fire Alliance. But there's others. There's the Canadian Wildfire Sat and a few other outfits that are working in this space. So I'll jump into the fires and get to the tech later. So you're no doubt aware, but it's always worth mentioning that climate feedbacks are pretty influential, both warming and cooling feedbacks, and many, I should say, are accelerating as the climate warms. So climate feedbacks are basically any process by which our direct emissions are kicking off other aspects of radiative forcing or emissions around the world. Like I said, these are both positive and negative. The biggest negative one, of course, is like CO2 fertilization of forests, or one of the biggest ones anyway. The sort of positive emissions, things that continue to warm, that accelerate warming, are things like wildfires. They're things like permafrost thaw, wetland methane is a big one, changes in albedo, etc. And these feedbacks are really important for a variety of reasons. One, they're just interesting, right? I mean, the biosphere is always interacting with the climate, so it's kind of just interesting to study. So they're kind of cool in that sense. They're interesting. I mean, this is the math group. They're interesting mathematical processes. These sorts of feedbacks are nonlinear feedbacks. They're all interacting with themselves as well as our emissions is interesting. But they're also interesting from a policy and like, what do you do about it point of view, because these feedbacks are not really incorporated into global models, which are used to drive climate ambitions by nation states, by countries, by the IPCC. And there's a good reason for that. It's because these climate feedbacks are not direct emissions, right? They're not us burning fossil fuels for a car. They're not natural gas for heating a house or running a steel plant. And so it's hard to say who's like responsible for this. It's hard to say, well, it's your fault, that wetlands are releasing more methane, Brazil, because it's not really their fault, right? And so in the international reporting and national greenhouse gas inventory space, so in the space where countries report their emissions, they don't include these. And they don't include these by, not really by law, they don't include these by treaty, like they're explicitly excluded. And so when we think about our trajectory of climate change, like going towards the Paris Accords, the SSPs that you see, or the RCPs, like the models which project future climate change, they may or may not include these depending on the model that they use. But the reporting the countries use to say how they're making progress against those scenarios definitely doesn't. And so this creates a real challenge. And that is, should we manage them? Should we think about them? What should we do about them? And so that's the fire problem. And we know fire, a variety of feedback problems, but fire being one of them. We know that climate change is making fire a little more touchy, a little more dangerous, a little more of an issue. Because while it's hard, as you'll see, there's a lot of variability in the trends in actual fire occurrences, and we'll get to that in a second. There's a pretty inarguable increase in fire weather. Fire weather is getting worse. We know climate change is causing an increase in fire season length, which is this graph, but also low humidity days, biomass available to burn, vapor pressure deficit, et cetera. So these are a bunch of graphs from Jones 2022 looking at fire season length, with the black line showing the trends and the red showing departures from the trends over a certain period of time where things got worse quicker, or projected trends, and then over the red is over the recent observed, I should say, where things got worse quicker than anticipated. This is expected to drive a lot more fire. Obviously, fire weather fire follows fire weather, and the increase in fire in the boreal, just in North America, is so a fairly small fraction of the globe, is expected to result in us basically burning off 3% of our remaining carbon budget. And some of the results that we have suggest it might be a little bit larger than that, depending on how the future goes. But it's not a small fraction. So that's the evidence that that's the suggestion that climate change is going to make emissions worse. Now, there's some nuance here when you look at the stats, and it's always worth mentioning, because when you look at the stats of fire emissions, it's not quite as straightforward as this would imply. This would imply things are getting uniformly worse everywhere. Like there's just more fire everywhere all the time, right? Well, it's not. We have to mention the human nuance, because fire is very much a human phenomenon. I mean, if you want to sort of put it in perspective, people have domesticated the dog, for 20, 30,000 years or something, right? But quite a while, right? Dogs been around for a long time. We've been using fire for like 5 times longer than that. We've been domesticating fire for, about 1 million years. People have been using fire for a very long time. So fire is very much a human phenomenon. So while we certainly do see increases in what are termed climate-driven wildfires, so like lightning fires that have nothing to do with people and tend to burn, which is on the left, we kind of see increases, red being an increase, and this is burned area associated with climate. We do see a decrease in human-driven wildfires. We're actually setting less fires as a species now. And so what that means is there's actually a sort of a mixed bag when it comes to net change in burned area. In fact, burned area has generally been trending down. And I say this sort of to head off some criticisms that may not be thinking about climate, because it's a thing. But when you look at wildfire emissions, so just wildfires, climate-driven wildfires, so you exclude that human decline, you see that wildfire emissions in forests are increasing. So there's been about a 60% increase in forest fire emissions since 2001. Almost all of that has been driven in the boreal, with a little bit in the tropics. So in these, I don't know if you can see my pointer, but in these globes here, there's burned area in the upper left, and fraction of burned area in the upper right, and then the bottom row is carbon emissions, both overall and as a function of per burned area, so relative. Brown is more fire, green is less fire. And so if you look at North America, for example, it's mostly brown, both in terms of burned area and forest carbon emissions, with a little bit of an exception around sort of Southeast Canada, although many of those places burned in 2024. And the increase in emissions is very high in Russia, as well as a little bit in the tropics, and then again in North America. So that's forest fire emissions. So those have been going up a lot. But there's other forms of fire, and for completeness, we should mention them. Agricultural fires, it's actually really hard to know. So this is a satellite problem that we'll get to again later, but it's actually kind of hard to know what agriculture has been doing well. I mean, we think it's been going down, and that's because we see a decline in emissions that you'll see in a bit overall, but it's actually kind of hard to tell. I mean, if you look at for the agricultural bread baskets of the world, you do see there's still a lot of fire in those areas. On the top is a map of emissions estimated in terms of grams per meter squared per year. So it's just a relative sort of intensity metric. We see a lot in like the Sahel in Africa, as well as the Southeast US and then Southeast Asia. The bottom is a map of what's estimated to be purely agricultural fires. That's unpublished at this point, but it's purely agricultural fires. And there's a decent amount. The reason I say it's uncertain is because we tend to map fires with platforms like MODIS or VIIRS that have some temporal frequency, but tend to be pretty coarse. This was a study by Ramo a few years ago that used Sentinel-2 data and got down to 20-meter resolution. And they compared these MODIS, I think it was MODIS, they compared the MODIS burned area map to this map that they painstakingly created at 20 meters and found that, or estimated that the coarser satellites were missing 80% of the burned area in sub-Saharan Africa. Like, it was just a lot bigger. And so they estimated the emissions were actually like almost could be up to double what was being estimated for Africa. Now, there's a good chance this is a bit of an overestimate just based on methodological choices. But that's not really the point. The point is that there's a lot of fire that's going undetected, especially in agricultural regions, because the fires are too small to be picked up on our typical fire sensing satellites, the MODISs and the VIIRS. The other problem, which this does not get to, is how short duration fires can be. And so agricultural fires may only take an hour or two to occur, and if you don't have a satellite flying overhead, you might miss them. So that's another reason why I say agricultural fires are still pretty unknown. We can pick up the big stuff we see in the Western US and Canada pretty easily. It's these smaller ones that we can't get as much. Lastly, the peatlands are sporadic. So the peatland feedback, or the role of peatland fires in global climate can be really significant, but seems to be much more sporadic. So in 1997, there was, if anybody remembers, there was some major peatland fires in Indonesia. And at the time, they estimated those emissions were like, well, they were huge, 13 to 40% of global emissions from fossil fuels, like just a dramatic amount, like a couple gigatons of carbon. There's been some sort of revisions on those estimates lately, some sort of like recalculated emissions factors, which have reduced that number by maybe 50%. And it's still potentially around a gigaton of emissions. Now, the thing is, this happened in 1997, and as everyone knows, fire history seems to have started in the year 2001 with the launch of MODIS. So we just missed this one with the MODIS record. So obviously it's on Landsat. I'm being a little facetious, but when you see a lot of graphs of trends, they start at 2000 because that's when that record started. Well, peatlands have this ability to sort of pop in and out, and when you get a big fire year in peatlands, you can lose a lot of emissions. So it's another sort of process that we need to better capture. So if you add all those things together, where does that leave us? So wildfires, ag, and peatlands. Interestingly enough, emissions have kind of been trending down since the year 2000, although the last couple of years have popped up again. If you look, I'll start on the right. If you look on the right with the bar graph, that's the total wildfire emissions in carbon as estimated by Copernicus in the EU. And you can see there's sort of a general downward trend. This is usually attributed to declines in agricultural burning. So, because as you'll see in the next slides, I'm going to transition to just talking about where we know the feedback is happening, boreal forests. So this is usually interpreted as a decline in ag burning, which is why I had that little digression about how hard they are to see. But anyway, this is the trend as typically reported, which is a general decline. But the last couple of years have popped up. And this year, if you're curious, we're actually a little bit below average this year as well. The graph on the left is cumulative weekly emissions, also calculated by the same, by GWIS, so sort of the same organization or more or less. The red line is us as of 2 or 3 days ago. I think it was December 4th or something. Blue is the average. So we're a little below average right now, but we're still well within sort of the historical envelope. Okay, so back to fires and the fire feedback. We have seen an increase in in wildfire emissions from forests globally. since 2000. This is perhaps best exemplified by the 2023 and 2024 Canadian wildfires. This is data from the 2023 wildfires, mostly in sort of Western Canada, sort of Alberta area. That year saw just an incredibly large increase in carbon emissions. The top are two maps. One is the average from 2019 to 2022, and on the right is just 2023. It's measured in carbon monoxide because that's often how carbon emissions are estimated. It's relatively easy to sense. Those emissions were dramatic. They're roughly similar to India's national emissions, just from the wildfires in that year. So that's a big deal. That's quite a large fraction. And you might ask yourself, okay, it's some emissions. Like, why do we care? Like, not why do we care, but it's fires. It's not tailpipe emissions. It's not factory emissions. Well, we care because these feedbacks, what we call indirect emissions, because they're not really directly human caused, but they're indirectly human caused. They add on, right? They reduce our time to these Paris targets. And from a policy point of view, that's really meaningful. Because while, scientists realize, we all know, the 1.5 Paris Agreement goal or the 2.0 Paris Agreement goal, there's nothing magical about those numbers per se. They're just sort of places we don't want to go because we know that the possibility of tipping points or negative impacts of climate change just get worse as you pass those thresholds. They're useful policy thresholds. And yeah, the exact number isn't as important as the symbolic policy value, but that's really important. And these feedbacks are going to reduce our time towards hitting those targets substantially. And like I said at the beginning, they're not included. And so it's essentially like a gap, like a blind spot that we need to deal with. We estimated, this is a paper that's in revision, we estimated that fire, along with wetlands and permafrost, reduce our time to crossing these thresholds by about 25%, just the additional emissions from these things. So that means we need to increase our regular emissions to deal, our climate ambitions around direct emissions to deal with it. But also means we should think about managing these, right? Yeah, I'll just go this one. So how do we manage fire emissions? How do we think about dealing with these excess emissions? Because they are going to impact our climate goal, and wildfires specifically, we do see going up, especially in the boreal. Well, there's a couple things you can do about it. Well, there's really two options. You can focus on direct emissions reductions. So we could just focus on increasing our climate ambitions, like our let's phase out fossil fuel ambitions faster, to pick up the slack or pick up the gap associated with these unaccounted for wildfire emissions, with these wildfires that should be incorporated, these wetlands that should be incorporated, permafrost, etc. We've estimated that you get about a 5 to 8% reduction in the strength of these feedbacks for every unit of direct emission reduction you reduce. So for example, if you were to reduce global temperature by about 1 degree, for example, through direct emissions reductions, it's obviously a really big number, but imagine you could, you'd actually reduce it by like 0.05 or 0.08, like almost 1 degree and almost 1/10, because you'd be reducing the strength of these feedbacks. So that's one option, is direct emissions reduction. It's probably the most palatable option because that's the most straightforward. That's getting to the root cause of the problem. The other option is management of these indirect emissions. And so that means directly managing the additional emissions from these ecosystems. And here on the slide, I said it's a fraught decision because you're basically saying we got to intervene in what's ostensibly a natural system to reduce its emissions. But the idea is not so much getting rid of fire. We've tried that before. It didn't work very well. But getting rid of the additional emissions, addressing and managing the additional emissions. Now, for wetlands, that's a tricky proposition. You're talking about managing natural wetlands. People understandably get a bit concerned. You talk about managing permafrost, it's hard to imagine how you'd even do that. Fire, though, fire management's not new. People have been managing fire, like I said, for 1 million years. quite literally in some areas. Indigenous communities have been burning the globe for tens of thousands of years. Where I grew up in the Pacific Northwest, there's whole islands that would get burned to increase forage for deer, for prey, increase berry production, things like that. Indigenous communities around the world burn things. It's an easy way to manage your landscape, and so people do it. There's also, of course, prescribed fire, which we see around here in Boulder sometimes from up the hill, but we see them sometimes. That's intentional burning. There's also suppression. The U.S. and many industrialized nations after World War II specifically, but really starting around the 1910, 1912 time period, thought we should just put these things out. And then with World War II and rapid industrialization, they suddenly had the power to do so. And so the U.S. had this thing called the 10 a.m. policy, where every fire was put out by 10 a.m. And if it wasn't, they made a plan to put it out by 10 a.m. the next day. And if it wasn't, they made a plan to put it out by 10 a.m. the next day. So suppression is possible. We can do it. We've learned our lesson. Complete suppression just bites you in the butt later, but we can do it. And then there's other things like thinning or mechanical treatments to reduce fuel loading, which is another attempt to sort of reduce the severity or likelihood of fire. So fire management isn't new. And so in the context of these bioclimatic, this bioclimatic feedback and this thought that maybe we should be managing these indirect emissions because they're just going to increase as the globe warms. So we need to, think about this as an additional source. Think about how it's going to affect our climate ambitions. Maybe we should manage them. It brings up the question: should we manage fires for these excess emissions, to reduce these excess emissions at a global scale? Well, where would you do that? Well, as I showed you earlier, this was the same map as from earlier. The boreal is the place where carbon emissions have increased the most when it comes to wildfire. So like I said, globally, wildfire emissions have gone up 60%, climate-driven and non-human. Wildfires gone up 60%, but the boreal is responsible for the lion's share of that. Boreal emissions in some areas have gone up almost 200%. Mostly this big swath of eastern Russia and the western North America. And the thing with this, and the reason this starts to make you think about, well, maybe we could manage this, is 60 fires or so were responsible for 75% of the burned area in the California wildfire, in the Canadian wildfires. So it's a relatively small number of fires. But the question is how? You'd think, well, maybe. How would you even start doing that? Well, the boreal or forest management is in its infancy in the boreal. I'll come back to that. I put a star next to infancy because there's actually a long history of indigenous fire management in the boreal as well. Whether that was through intentional repeat burning of a landscape, like to keep meadows open, or thinning and prescribed fires around communities. There's a long history of this. There's many communities, especially in Eastern Canada, would light fields on fire for the same reasons they did in the Northwest many times, like to increase berry production or increase forage or to make it easier to hunt. And they would do this every year or every couple of years. And if they had to leave before, this is a story from a recent paper by Amy Cardinal Christensen, who's an Indigenous researcher in Canada, a great one. They would, if they had to leave before everything was dry enough to burn, they'd just make a big fire and put some logs sticking out of the fire that would smolder. So when stuff did dry out, it would burn out into the meadow and set it on fire. The reason I put a star next to it, though, and said, it's still kind of in its infancy, is the scale at which this occurred is still kind of questionable. And we're talking about managing things of relevance to a global scale. That becomes a little more difficult. It's one thing to do this in small areas. It's another to think about doing this at scale. But pre-fire treatments like thinning and repeat burning do have a history, and it's worth mentioning. But the thing that new technologies are making possible, or at least, I'll take that back, not making possible, but hint at what might be possible, is things like targeted suppression. So bringing back that suppression paradigm a little bit, but learning from it. The idea would be if you can identify significant undesirable fire early, like before it turns into a big conflagration you can't fight. If you could identify fires that are likely to cause major emissions, and you could attack them before they grow too large, you could reduce that big bump of emissions associated with these feedbacks while still allowing fires that aren't likely to produce massive emissions, still allowing them to burn, because we know that eliminating fire from the landscape entirely is a very, very bad idea. This is of interest, like at the Canada scale. This is a graph of total CO2 emissions in the forest sector in Canada, and the gray line is the total from 2016 to 2022, and then the 2023 ones just blow their typical emissions completely out of the water. That's just the fires, that's not everything else. So this makes you think, well, if we knew, you can't know ahead of time if fire is going to happen, obviously, but if we knew very quickly what we could do, maybe we could act on it. And that's where the new satellite technologies come in. And this is pretty exciting from a space network point of view, because the satellites that are now being put into space for fires are really tailor-made for this, and to some extent, because the motivating factor for many of these new satellite systems, from FireSat to Aurora Tech stuff, even to WildFireSat in Canada, and I'll show a couple specs in a second, is really rapidly identifying fire starts so that managers or firefighters, first responders, can put them out. And that's not really, was not envisioned necessarily for wildland areas, more for like buoys and avoiding the next Marshall fire or the next, LA fire or something like that. But it's the same sort of tool, right? And so you could see that this could enable really rapid action. So what do some of those things look like? Well, WildFireSat is a satellite system that Canada's putting together. It's scheduled to launch in 2029. They're aiming for 7 satellites that get, I believe, 7 observations per day. With basically their goal is simply to identify fire starts quickly, and then provide fairly real-time data to first responders. The one I'm more familiar with is FireSat. This is being run by Earth Fire Alliance, which is a different organization, but we're collaborating on it. The FireSat concept is very similar. It's to give very high resolution, both in space and time, imagery to first responders so people can manage fires better, both for community protection, but also for climate purposes. It actually started through EDF, through Environmental Defense Fund, my org, sort of helped spec it out along with Muon Space, and then Earth Fire Alliance took over the running of it. Now they're doing all the hard work and get all the credit. They have 1 in space now, a protoflight with 3 more to launch middle of next year or so, and they're aiming for 50 by 2030, which would give you a 20-minute or so revisit time anywhere in the world, 24 hours a day. Now, one of the exciting things about FireSat, and one of the things that makes you think, hey, this could work, is it has a 5 by 5 meter, it has the ability to detect, or should anyway, have the ability to detect hotspots down to about 5 by 5 meters. So quite small fires, meaning you're identifying these things really, really early when you can do something about it. And I say should because there's only a protoflight up there. And so these are the sorts of scientific needs. We need to build trust in it. We need to test it. And we have, because there's only a sort of a prototype up there right now. It's a fully functional satellite, I should say. It's just called the protoflight because it's being used to sort of test all the bugs. But it can see, it should be able to see a 5 by 5 meter hotspot. And actually, this is a really exciting shot. It doesn't look like much, but there's signs that it'll work. This is a fire the protoflight saw in eastern Oregon, or sort of central Oregon, near Medford. Well, actually, that's more western Oregon. Sorry, along I-5 in western Oregon. It's just that little orange dot, so it doesn't look like much. But the thing that's cool about this fire is no other satellite system saw it. So this is a satellite that MODIS missed, that Beers missed, that Sentinel didn't see. And so why didn't it see it? Well, this fire was started by a truck dragging some chains down the side of the road and effectively just burned someone's front yard. Like, it wasn't a big deal. It was a small fire. It got put out really fast, just on the roadside. Not a big deal. It was only lit for, a few hours. It didn't take very long to burn. And so the other satellites missed it. Either they didn't fly over at the right time, or it was too small, or what have you, but they missed it. And they actually, EFA had to go and do this hard work of like tracking down the police reports just to verify it was an actual fire, but they did. And obviously small fires, grow into big fires. And so this is kind of exciting. So we still have some key questions that we need to answer going forward with the satellite, because we need to understand, or not with the satellite, with this strategy of addressing fire emissions, and it involves the satellite, which is like, what makes for a high emissions fire? Like, when you're thinking about a climate impactful fire event you may want to control, what is it? Is it because it's burning on substantial soil carbon reserves like permafrost? Is it because it's particularly intense? Is it because it's likely to grow into something particularly intense? What constitutes a fire event? Does permafrost thaw after a fire count as fire emissions? No one's really ever quantified that or really put that into a framework, but it's an important one. What's the timeline for response? Like, how quick do we need to find these things? This is kind of a mathy question, but it's basically, how fast does the fire grow, and how quickly do you have to have resources there if you actually want to do something about it? There's a sort of Forest Service phrase: you fight a fire in the first second with a spoon, first minute with a bucket, and the first hour with a truckload, right? And past that first hour, it becomes a much harder task to fight a fire, especially in like a windy event, or a droughty event, or in conditions that are likely to be bad. And then we need to understand what's an effective response. What's the effective way to sort of manage these fire emissions if we want to cut off that fire feedback. So what we've been doing to answer those questions at EDF is we've been pulling together the broader scientific community, and I'd love to hear your thoughts too, on how these new tools, these new satellite tools, whether it's FireSat or WildFireSat, or even non-satellite tools like we're currently funded by Google AI to do some stuff with machine learning and try to understand fire behavior that way. What do we need to do so that as these new tools, like the satellites, come online, and they're all coming online around 2030, 2029, 2030, that we're in a place to take action on emissions and reduce them? What's the place we need to be in? What do we need to understand? What do we need to have like a predictive framework for, so that once we see them, we can do something, or at least decide whether we want to do something. So we've been having many meetings with hundreds of scientists and specialists come in and give their thoughts on how to build confidence in these new tools. I was talking about it before the call. Like, what's the radiative transfer modeling we need to do to sort of build expectations and understand that, hey, what's happening on the ground is really what the satellite's seeing. Well, that's a capacity that we need to develop over time. But it's also things like carbon emissions. When we see a fire, you're not actually seeing the CO2. You still have to understand how much of that energy is being converted into carbon emissions. And that's not necessarily a simple task, especially when you have a totally new satellite system that has a different resolution than anything that came before it. But we're working on it. And we're working, and I'm actually ending with sort of the big vision, which is science that should empower this sort of strategic thinking before a fire and rapid event response during a fire to minimize emissions while allowing for that sustainable natural fire regime. And it's a huge problem, from optics to logistics to policy, but it's also a lot of just good old-fashioned, modeling and math, trying to understand how these things propagate, how they build, what constitutes a big event, and how much control we want to take over these excess emissions. So that's it. I wanted to leave a lot of time to chat about FireSat or wildfiresat or uh, or any of the emissions questions.
Okay, awesome. Thank you, Brian. That was really interesting. And see, find the clapping emoji like I usually do there. So yeah, please, everybody, let's thank Brian. And yeah, we have lots of time for questions. So we've got enough people here. Maybe raise your hand if you have a question.
I think that's something.
Ethan, I think. Maybe not. Sure, Olivia.
I just wanted to give Ethan a chance just in case he just figured out how to unmute. But okay, if not, hi, that was a great talk and thank you for sharing. One of the questions that came up for me is you started off a lot talking about management practices at the beginning, and then you sort of, oh, Ethan says just clapping. You sort of switched into talking about, I guess, like incident management. So I was curious your thoughts on, I guess, the extent of our ability to impact emissions from a management perspective versus a like responding to large fire incident perspective. Does that question make sense? I
think
keep talking.
so. It sounds like you're sort of asking about our ability to manage fires in a pre-fire condition versus during the fire.
Right, and it seems like, I mean, that this FireSat technology is super cool, and the 5-meter by 5-meter resolution is really impressive, and it seems like that is really going to help us with that during fire regime, but not necessarily the pre-fire regime.
Yeah, I think that's an open question. The reason I switched is there's different ecosystems which are more conducive to pre-fire management versus sort of incident command, and at least to me, and I know people disagree with me, so that's I know of people who think this is not as big of a deal as I think it is, but I think pre-fire management in the Boreal is going to be a hard ask because the area
I was wondering.
It's a gigantic area, and so from a practical point of view, I think we need to consider both options. We're not going to be able to rely on pure pre-fire sorts of options. We need to consider both. That may be a different calculus, like in Colorado or California. You have a lot more people, and you can be proactive if you had the resources, the money, and the social acceptance to do prescribed fires every year. You could go a long ways towards solving at least many structural issues. I mean, I really wish we had more prescribed fire here because we just have a lot of fine fuels that need to be controlled.
Yeah.
But yeah, in the Boreal or in tropical areas, some tropical areas, the ability to do that at the relevant scale, I think is a open question. Like, can you really do that? Now, the second part of the question was, can FireSat help with those things anyway? FireSat is definitely sort of designed to be an incident-oriented thing, or at least that's where most of its first order sort of impacts will be. The bands are intended to basically see through smoke, get a good sense of fire radiative power, so you know what behavior is happening at any given point in time, and get that to incident commanders so they can manage it, right? Like, your intuition is right. That being said, I think when we have a few years of data, it will be useful for pre-fire management because it'll be able to tell us with a resolution we haven't had before how effective those treatments were. You know, like one of the challenges with MODIS or VIRS is they do have fire radiative power, so you can get a sense of intensity, but they don't have that temporal resolution. You're getting like a couple shots a day. Even when you put them all together, you're not getting the best picture. If you had a 20-minute time slice of like how a fire burned from a grassland into some place that had been burned, like prescribed fire, or a place that had been thinned or whatever, you get a much better sense of how stuff behaves at a better spatial resolution. So I would call that a second order thing because you're going to have to build it up and actually do that science. But I do think in the end, it's going to be really useful for evaluating pre-fire treatments, but not right away, like you're saying.
Yeah, cool. I hadn't thought of that. That's a good point. Thank you.
Yeah, I'm excited for that because fire is such a dynamic thing that when you work with like the MTBS data or these things which are basically like either pixel based or even day based, you're just missing so much of the story that it's really hard to know.
Mm-hmm.
And much of the promise here is getting a much better understanding of fire behavior. And obviously some fires are studied very well with aircraft or whatever, you have videos of a lot of fires. So it's not entirely unprecedented, but it will happen globally. And so we'll have a much better view of how these things are happening across a lot of events.
It would also give you a really, like, I know some, one of our ways currently for understanding effects of fuel treatments is just using physics-based models or operational models. This would give you like a really nice validation data set for understanding if those tools are actually giving you realistic results, because you could literally see what happened in an area that was burned and then compare that to what we're getting out of our models and see if we're actually getting any sort of reasonable information from them.
Totally. And it's not like it's going to replace ground data. You're still going to have to go in and validate and measurements, but it'll allow you to actually do that and then extrapolate it in a much more powerful way.
Yeah, cool.
Okay. Yeah, one.
Hi. I missed the first quite a chunk of the talk, so I might ask a question that you already answered. So with the I'm curious, with the bands available in the FireSat, can it measure other things like the AOD or look at vegetations and burn scar after fire?
Yeah, you can see burn scar pretty well. It's not going to do much with the AOD or smoke production or anything like that. But it can see burn scars pretty well, but it hasn't really been assessed. So this is part of the exciting bit and why I've been sort of giving this or versions of this talk in different places, is because we want people to think about this as an emerging tool, have this on their radar. Because this wasn't designed for that. This was designed for seeing fires and quantifying fires. But there's no doubt a ton of things you can do with it scientifically that we need to test out. We need to see how well it works at mapping burn scars. There's been, I don't have the picture on this slide deck, but they have looked at old burn scars using FireSat in Alaska. And it picks out old burn scars pretty well. The bands, though, weren't really optimized for that, so I think it's still an open question how well it's going to do that.
I see. Can it see the smoke? Like from these images, I feel like I can see the smoke from the fire.
Yeah. So this is just a true color image. This is the these are the images. So yeah, you should be able to see it in in the red band and the near infrared band. Smoke is going to obscure things a little bit. But it's not like a spectrometer that's like trying to get at like composition of the smoke plume or anything like that.
I see. So can I use FireSat for sending alert to residents of where the smoke is predicted to be or things like that?
We're hoping we can. Yeah, we're hoping we can. One of the workshops we put on this summer was entirely with community health and smoke specialists, basically. And while this isn't really optimized to like see the smoke plume in quite the same way, I mean, you can see it some, but it's not like it's trying to get at the chemistry of the smoke plume. We are hoping that the much improved information on fire radiative power, not just at one point, but over the course of the burning event, so hey, it burned for 3 hours and the integrated radiation was X, will give us a lot more information on what was volatilized and how high it went. So it's another one of those sort of second order products, but we are hopeful it will, because you'll have a much better sense of where the fire was and where it burned hot, especially when you get into heterogeneous environments like the WUI, like the LA fires. It's hard to burn structures. You'll be able to see that with this much better and hopefully get a better sense of how much smoke's produced, how bad it is, and in conjunction with other missions and other products like wind currents and wind products and stuff, get a sense of how you might warn people that this is a bad event or this is a less bad event or whatever. So on its own, it's not going to solve that problem, but it could be a better part of the solution, or it could make for a better product in conjunction with other stuff.
And then say for the this is the orbiting satellites, right? So
Yeah, these are orbiting. Yeah, they're not
So-
geostationary, they're orbiting.
so then say I want to monitor a area to see how the fire events evolve over time, like then how do I see that 3 hours or 4 or days of events? Does
Yeah.
it-
Yeah. So this is something where if you have feedback, let me know, because this is actually still being worked out. So this is mostly a preview of coming attractions. Like I said, there's a protoflight up there now. There's 3 more next year, and I think we have 3 more right after that, shooting for 50 by 2030. So they're still trying to decide on the best way to distribute data. The way they're planning on rolling it out, and I'm speaking for them, so I'd have to, if you have any specific questions, I'd have to ask, obviously. But the way they planned to roll it out is in these focal areas. They're focusing first in Australia, the Western US, Alaska, and Southern Europe. And so those areas will start to get the data rolled out first, hopefully starting mid next year. It will be free to researchers, and it'll be free to first responders. They're going to have other groups will probably have to pay for it, for-profit groups, but researchers and first responders will get it. Again, they're not quite sure how, like where you go. Like, would you go to firms, or would you go to Google Earth Engine or something? That's not quite clear yet. But ultimately, there will be this global repository that you can then just go and download. Yeah, download scenes, much like you do now.
That's great. So then in that case, how far back the FireSat data that a researcher can get? So say if I want to study FireSats matching some of the big fire events that has happened within the past 5 years, how much back in time I can look at?
Not very far.
Okay.
Their first protoflight just launched this spring, so you
I see.
really saw the first data.
Okay, thank you. Yeah, it's a very interesting data set, and I've been trying to find fire treatment mitigations data sets and
California has a good
been
mitigation
fun.
data set. California's putting together, or has put together, a statewide. I mean, it's California, so it's a very particular fire regime, but California has a good one. Yeah, but as far as this data goes, like I should always say, Earth Fire Alliance is running it, and so they control it, but they have committed to making it free to researchers. It's somewhat of a slow rollout because they're trying to do they're doing all the validation right now, and so we're trying to sort of increase exposure so people are interested in it.
Okay, great. Yeah, thank you for your talk.
Thanks, Joan. Any other questions for Brian? If not, I have a couple. One thing that I thought was pretty cool, the size of that small fire that was spotted is really interesting. Yeah. I guess one sort of general question is, are there enough of those that when the satellites miss them, we're not accounting for all the CO2 emissions from fire? That would be like a significant amount. I guess that's what maybe find out, right?
Yeah, I mean, I guess that's what we find out. I mean, there is fire emission inventories, based on just carbon monoxide production that's seen. But but in those global budgets, there's a lot of flexibility. There's a lot of degrees of freedom in there, and so if you go by the Africa study I mentioned here, that would suggest we're missing a lot. The fact that these MODIS inventories are really, really incomplete, and you bump up the number almost double when you go down to 20 meters. Well, what if you start accounting not just for this better spatial resolution, but much better temporal resolution? It's a lot of these fires, the ag fires, especially in Africa, are very short, like on the order of hours. Well, we're missing a lot of those, and I don't really know. I think it's a very open question, but this would imply that we're missing a lot. If you take there's obviously an upper limit, right? But but understanding how to deal with fire emissions as part of this like global, just understanding how our atmosphere works and how we manage our global temperature, getting a better handle on how much of these small flashy sorts of things and what fraction is important, because that tells you the size of any sort of policy that would target those or target other things. It sort of narrows down the opportunity space. From a historical perspective, if like the adoption of MODIS is any indication, and sort of the fire satellites that came on in the early 2000s, or the fire relevant satellites that came on in the early 2000s, really shocked people, because they're like, there's no way there's that much fire, like in the eastern US. No one thinks of the eastern US as having that much fire. And it was shocking. Many people thought the sensors were just, not quite right. They weren't. There's a lot of fire. And so I would expect this would be a similar sort of revelation, because we really are starting to unlock, not just with this, with Aurora Tech, which is a commercial satellite that does a very similar thing, and they sell their data, or with FireSat, but with these sorts of high temporal resolution satellites, I think we're going to start seeing the same thing. Like, oh, there's a lot more flashy fire than we thought there was. And I'm really excited for that. I think that's going to be absolutely fascinating.
I suppose this isn't quite a question, but to some extent, not all emissions from fire are emissions that we would want to get rid of, I assume, just because there's going to be a positive feedback with like prescribed fire. And I don't know a lot about the emissions budget, but like that's fire that ultimately I assume will result in lowered emissions from catastrophic fires.
Yeah, I think that's debatable. It depends on no doubt where you are. A lot of the, but it's well, first off, you're correct, right? Like, no one would want to get rid of all fire emissions. That would be foolish. That would just create bigger fires later. Like if you go to the complete extreme of eliminating fires, that would be self-defeating. No one would want to do that. And then in many parts of the world, you may need to increase sort of a slower level of emissions to avoid large emissions. Now, whether that would result in an increase or decrease of like net emissions, I think just depends on the likelihood, on how much area you have to treat and how likely a big fire is. If you look at the paleo records of California, for example, its historical carbon balance, it seems to be in most places I've seen that have been studied under indigenous management, its carbon balance is much lower than it is now. There's a lot less carbon in the landscape. That would imply that increasing our fire to reduce catastrophic fire, like increasing the strike fire, would probably result in more emissions overall. But that's not the only management goal. Emissions aren't our only management goal, right? Like there's a lot of people there. They want to avoid these catastrophic fires, and that's a perfectly valid thing too. And so it might be worth trading some more sort of lower level emissions to avoid those catastrophic home destroying fires as well. So I don't think anyone would suggest that emissions are the only goal or should be the only goal. But it is a goal, and it's definitely something at a global scale we need to consider as this and other feedback start to become like a relatively significant player in our overall net forcing on the atmosphere away from historical levels. I mean, many of the ways I think about it is just like, can we keep fires at the baseline level of, and avoid this positive feedback? Now, baseline level is a squishy term in and of itself. And so you still have to kind of pick one. And that's always open for argument. But I think that the gist of it is just trying to avoid that increasing emission trajectory.
Well, thank you.
It looked like you were responding to the baseline level comment before I caveated it.
Yeah, I think I didn't unmute myself, but yeah, I was going to say baseline seems like I was going to ask where that came from, but then
it's a judgment. Yeah, no, you have to make a judgment at some point, right? Like,
yeah.
And that's just the way it is. I mean, the fun thing, I was in paleoecology for a while. I collaborated with a lot of paleoecologists for a while. And you can find an interesting fire regime almost anywhere. You can find a huge variety in fire regime almost anywhere, I should say. So, yeah, to some extent, it's a management goal. But like I said, fire and humans have been a hand in glove for hundreds of thousands of years. So,
yeah, I don't envy you looking at this from sort of a policy perspective as well, because that adds in just like a whole layer of complication that Seems hard.
Yeah, I mean it is, and it's, I think fire is an interesting policy challenge because there's often mutually conflicting goals that are both good, you know. So like you may want to increase the rate of fire because you want to increase prescribed burning, you want to decrease the probability of some catastrophic event that burns homes, or you just want to restore a natural fire regime that tended to be high frequency, low severity, like in Arizona, or some other reason, whatever. You know, there's a lot of good reasons to have a lot more fire. If you're an air quality person, even exposure to low levels of smoke is really bad. It's not like having a big plume is bad for you, but low levels of chronic exposure is good. Like chronic exposure, even at low levels, is quite not good. You know, is from a public health perspective, is not ideal. And so you have legitimate people that are saying, hey, you know, we have vulnerable populations. We cannot have low levels of smoke all the time. And then you have other people that say, hey, we are so far behind on our fire that if we don't have a bunch of prescribed fire, we're in real trouble sooner or later. Those can be in conflict. And so it is a difficult place to find a policy where everybody can be happy. And then you have prescribed fires that get away. And that doesn't happen very often, but it's certainly publicized.
Yeah.
Like it was.
I was
And
living in New
so-
Mexico when that happened recently, and
Yeah.
that is, not a good luck.
Happened in Colorado when I was in grad school. This is a while ago, I guess, but somebody died, and like they had to shut it down for a long time, and it is a hard place to operate. You know, I'm on the science side, so I can't even complain. I mean, there's people that have it much worse when it comes to trying to wrangle fire policy. We can just provide them with the best data, and this is the best data possible, I should say. And these sorts of new tools are going to be really exciting because they'll enable a lot more targeted management and data-driven management if we can build them out in the right way. But the policy to enable stuff to act on it is still a task also. But a lot of good people working on it. At least that's what we.
Okay, any other questions? I might just sneak in one more then. You mentioned some funding from Google to do some machine learning work for fire behavior, I think. Is the idea because that FireSat and some of these other satellites will have such good temporal resolution? Is the idea to train directly on observations, or is it to do what's often done to train a model, which is use a physical model, assimilate the observations, produce a reanalysis set that you can then use to train something that runs a little faster?
Well, some of the projects we're working on with Google is to understand how AI and machine learning can be leveraged to improve our understanding of climate, given FireSat, given all these new observations. And it's kind of there's space in there to understand where to go. I mean, they're trying to understand what's the potential of these new tools. And I could see that going in a variety of different ways. It could be sorts of reanalysis, sorts of things. It could be complementary stuff, because like to really understand how a fire is going to move, you got to know weather. You got to know weather real fast. Excuse me, if you're going to take action on it. And that's definitely kind of an AI task because it's fast, right? So I think the space is pretty open. I mean, there's a lot of potential here, and I don't know. I guess I don't know the answer to the question yet because it's such an open space. We're trying to find ways to better understand to better enable FireSat and other tools in conjunction with AI or machine learning to better understand the fire climate relationship and potentially better manage it. How we tackle that, it's still early days. So they're organizing a bunch of different groups. It's not just us. There's a bunch of different groups working around this because it's such a big task, and everyone's working really hard to try and figure out how to best make a difference in this space effectively.
Okay, so it's sort of more general, not just like fire propagation or something. That makes sense.
I'm sure there are people working on very specific physics-based modeling as well. Yeah, and I'm hopeful, especially with the fire radiative product power as this comes out, the FRP product, given that sort of high density time slice, it'll be really informative to those efforts.
Yeah, definitely. It would be really, yeah, be really fun to play with.
Yeah.
Cool. Okay. Okay. Any other questions, or we can set Brian free?
Well, hopefully it's interesting. Don't hesitate to ask me any questions. I'm happy to connect folks with EFA or Firelines for FireSat stuff, or chat about fire and climate.
Thanks
Yeah,
again for
thank
the
you very
talk.
much, Brian.
Yeah.
I'll watch the recording and then I will reach out to you
Okay.
after I catch up.
Cool.
Thank you.
Yep.
Bye.
All right. Perfect. Thanks, everybody.
Thank you.